Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today's the start of a new unit, and with it comes two important theorems, the mean value theorem and Rolle's theorem. And you'll see later on that these are very closely related. One is more of a subcategory of one of the other theorems. And by the end of today, I want you to understand what the initial conditions are that are required to use each theorem, what the conclusions are for each theorem, and then be able to apply the theorem to a variety of practice problems. So to start off, we are going to review what the average rate of change and the instantaneous rate of change are and compare the two. So pause the video, take 60 to 90 seconds, write in what the average rate of change for a function is and what the instantaneous rate of change for a function is. And you can talk about slopes, you can talk about tangent lines, secant lines, etc. All right, so I just put the answers down. The average rate of change is going to be the slope of the secant line between 2 points, and the instantaneous rate of change is going to be the slope of the tangent line at a single point. Okay, so now that we have those two concepts reviewed, let's now actually go ahead and review how to find the slope of a secant line, or the average rate of change. So f of x is given below in a table. This is a differentiable function, so you can assume that it is continuous. So find the average rate of change of f of x over the interval 2 to 12, and just show me your work below. All right, so again, average rate of change is going to be the slope of the secant line, which is going to be the difference quotient, or the slope formula, essentially. So we're going to have f of 12 minus f of 2 all over 12 minus 2. This is equal to the average rate of change. Well, f of 12 is 8. F of 2 is 5, 12 minus 2 is 10, so I get 3/10. There are no units, so we don't have to include units here. We just have to include the number. Okay, let's keep moving on. There is a reason why we're reviewing average rate of change. We're going to be using it later for one of the theorems. But the first theorem we're going to talk about is Rolle's theorem. So I'm going to put the theorem up here all at once, and then we're going to discuss it. All right, so I put the initial conditions in red, and I put the conclusion in blue. So if f of x is continuous on the closed interval a to b, differentiable on the open interval a to b, and f of a equals f of b, so the y values of the two endpoints of the interval are equal, then there exists a c on the open interval a to b such that f prime of c is equal to 0. I'd encourage you to pause the video and think about what this means. Maybe sketch out a picture yourself with these initial conditions and see if you can understand why this conclusion must exist given those initial conditions. Then we're going to work through an example ourselves to show you, but I think it's better if you try to think about this on your own first, because that'll help solidify the theorem in your own head. All right, so let's work through this example, and hopefully we now understand, or we will understand, why those conditions will lead to that conclusion. So it says graph the points from the function f of x above. So you can't see it on my screen, but you can look at it yourself. That is the table with those points. So we're going to quickly graph those points. We have 0, 1. We have 2, 5. We have 4, 8. 6, 10. 8, 11. 10, 10. 12, 8. 14, 5. And 16, 1. And it did say this function was differentiable, so I'm just going to sketch a smooth curve through it. Again, it may not look exactly like this because I don't know what's going on in between the points, but I do know that it has to be a smooth curve because it is differentiable. Part A says, draw a secant line between the values of f of 2 and f of 14. So we'll do that secant line in green, f of 2 and f of 14. Well, our secant line would look like that, right? Because f of 2 and f of 14 are both 5. And it says, why do these 2 points fit the initial criteria for Rolle's theorem? Well, f of a, right, f of 2, we could say, is equal to f of 14 because they both equal 5. We can also say that the function is continuous from 2 to 14, and it's differentiable on that open interval 2 to 14 as well. So we're actually going to write that underneath. So continuous on 2 to 14 and differentiable on the open interval 2 to 14. So those 2 points and the function f of x fit the 3 criteria for Rolle's theorem. So now we need to think, is there a point on the interval 2, 12? That should be 2, 14. It's already fixed on your paper. I'll have to fix it on mine. I also needed to make that an open interval, not a closed interval. So is there a point on that open interval such that f prime, or the derivative, is equal to 0? Well, take a second to think about it. Is there going to be a tangent line that's horizontal on this graph? And we can see that there is. It's going to be right at the maximum of the parabola that we drew. All right, so yes, at x equals 8. So Rolle's theorem here holds. The initial conditions were met, which means we should have a point where the derivative is equal to 0, and we did, right at x is equal to 8. So let's jump down to number 2 on the next page. Let's look at a different type of example. So I'm going to have you pause the video, work through these questions on your own, and then come back and join the discussion. Okay, so it says answer the questions about the graph below. Does the function below have 2 points such that f of a is equal to f of b? Well, many different answers here, right? And actually an infinite number of answers, because you could use fractions and decimals. But I'm just going to pick 2 easy points. f of negative 2 and f of 2 have the same value, right? They both are equal to 2. So yes, x equals negative 2 and x is equal to 2. Question B says, is there an x value, so or c, between your 2 points from part A such that f of c is equal to 0? Well, are we able to draw a tangent line such that it is horizontal on the function somewhere between those 2 red points? Well, we can't, right? If any tangent line to the left of 0 is going to look like this pink one, because the function is linear there, and any tangent line to the right of 0 is going to look like this brown tangent line here, because the function is also linear. Well, what about right at 0? What about right at that point? Could the tangent line be horizontal? Well, no, because the tangent line doesn't exist there, right? It's a hard corner. The tangent lines are approaching different slopes from the left and the right, if we think about the formal definition of whether a derivative exists at a certain point. But there is no derivative at x equals 0, and there's no place where the derivative is equal to 0. So no. Well, why not? Doesn't Rolle's theorem say that we have to be guaranteed an x value where the derivative is equal to 0, as long as we have those 2 points that have the same y values. Well, we got to think back to our initial conditions, right? Having the same y values for your endpoints is only one of the initial conditions, right? There are other conditions that have to be met as well. The function has to be continuous, which this function is, right? There's no discontinuities between -2 and 2. But the function is not differentiable on the open interval because it's not differentiable at x equals 0. So Rolle's theorem does not apply here because f of x, or whatever we want to call this function, we'll call it f of x though, is not differentiable on -2 to 2 because f prime of 0 does not exist. Right? And there are a couple different ways you could state that. You could say it's not differentiable at x equals 0, rather than saying f prime of 0 does not exist. But we have to be careful, right? All 3 initial conditions have to be met. So you just have to make sure you go through all 3 of those rather than just stopping after 1 or 2 of them. And when you're on when you have a free response question, you have to make sure you list all of those, right? Even if you know that the function meets those criteria, you have to state that it does, right? So you have to state the function is continuous on the closed interval. The function is differentiable on the open interval. And f of a is equal to f of b. And you would need to show what those 2 values are to show that they're equal. All right, so you guys can answer this question down below. Again, it just asks you to state the 3 criteria for the theorem, just because we need to solidify those, because we will need to use those when we're answering a free response question dealing with Rolle's theorem, or thinking about a multiple choice question that uses Rolle's theorem. Before we end part 1, because I'm going to keep the mean value theorem for part 2, I do want to go over, we may just go over both of these. They're asking you to determine whether Rolle's theorem can be used on the following functions for the given intervals. So you need to walk through those criteria and show that each criteria holds true. Or if one of those criteria doesn't hold true, you can just say that Rolle's theorem cannot be applied because a certain criteria was not met. So pause the video, take a few minutes to work through these, see if you can identify whether Rolle's theorem is applicable or whether it is not. All right, so we're going to do number 3, because for some reason I labeled these out of order. Remember that the first criteria is that the function must be continuous. So we can just say, this is not f of x, this is g of x. This is a polynomial, but we can just say that g of x is continuous on the closed interval -3 to 0. You don't have to state why it's continuous. Saying that it's continuous is enough on the AP exam. Number 2, we need to talk about whether it is differentiable. Well, we do need to show some work here. So we actually need to show what the derivative is, because the derivative, even if the original function is continuous, right, the derivative may not exist everywhere. So we're going to find the derivative. So g prime of x is equal to 18x minus 4x cubed. We can see that this is another polynomial. So then we can say that g of x is differentiable on the open interval -3 to 0. Okay, you just need to show what the derivative is so that the AP reader, whoever's grading your quiz, understands that you at least looked at the derivative. You didn't just say, this function seems differentiable, I'm going to write it down. Criteria number 3, we need to show that f of -3 is equal to f of 0. So if I substitute in -3, you don't have to write out all your work for that. Sorry, we should actually say g of -3 and g of 0. Keep thinking this function is f. It's not. You don't have to show all your algebraic work. You could just substitute this into the calculator if it was a calculator problem, or you could do your work off to the side or whatnot. But they're not going to need to see every simplification step here. But we do end up getting that g of negative 3 is equal to 0, and g of 0 is also equal to 0. Once we have shown that those three criteria hold true, we can then say, thus, Rolle's theorem is applicable, or applicable, depending on how you want to say that, on the closed interval negative 3 to 0. And we are done. Off to number 2. Hopefully you've already attempted this. We're going to check out the same thing. Our function is, again, g of x, and we have sine of 2x all over the quantity x plus 2. We need to check out whether it is first continuous. And because we have a quotient as our function, we need to check out if the denominator is ever equal to 0. Right? And we can see that g of x is not continuous at x equals negative 2 because the denominator is equal to 0 there. That being said, we need to make sure negative 2 is inside of the interval that they gave us, right? Because if negative 2 is outside, well, then it wouldn't matter because the function would still be continuous on that interval, even though it wasn't continuous everywhere. So we need to state that x equals negative 2, or negative 2 is on that interval. So g of x is not continuous at x equals negative 2, and negative 2 is on negative 4 to negative 1. I guess I can't be 100% sure that they're going to mark you off for not including that last part right here, but better to be safe than sorry. It does show a deeper understanding than just saying that g of x is not continuous at x equals negative 2. Because of what I mentioned before, we're looking at a specific interval rather than the entire function. So then we say, thus, Rolle's theorem is not applicable on the closed interval negative 4 to negative 1. And we don't need to check out the other criteria, because if one of the criteria is false, right, well, it doesn't matter if the other ones are true or false, because all three criteria need to be true for Rolle's theorem to be applicable. So we're done once we prove that one of those is false. All right, we are going to cut it off here for part 1. When I see you for part 2, we will be discussing the mean value theorem. All right, enjoy the rest of your day, and we'll see you back for part 2.